Welcome friends to this lecture of week 9 lecture of soil science and technology, and in this lecture we'll be trying to finish this soil erosion and land degradation topic, and then we'll be starting the universal soil loss equation. So in the last lecture we are talking about the control of erosion in constructed sites, and we talked about 5 different ways to control the erosion, soil erosion, and at the constructed sites. So let us see different types of ways to control this soil erosion in constructed sites, and these practices are generally performed in advanced developed countries, and nowadays some of these practices are also started in Indian condition also. So let us start with covering the exposed soil. You can see here this instrument is called the hydroseeders, which basically sprays a mixture of grass seed, straw, fertilizer, water, and sticky polymers, which ultimately establish vegetation in the difficult to access areas. So this is another way to control the soil erosion and covering the exposed soil. This hydroseeder helps in the spraying the mixture of grass seed, straw, fertilizer, water, and sticky polymers, and basically ultimately you can see this established vegetation in ultimately which develops in the difficult to access areas. And erosion control mats are also another way of fighting this soil erosion at the constructed site. You can see these are the erosion control mats which are spreaded, which are spreaded, and these mats are basically made up of jute, and these basically hold the soil and seed in place until the vegetation is established. So this is also very much important, which helps in reducing the movement of soil from one place to another place. So these hydroseeders and erosion control mats are important ways to fight against the water erosion and other type of erosion, movement of soil particles from one area to another area. So uh, uh, also you can control the stream bank erosion. Here this is an example of controlling the stream bank erosion. You can use hard and soft armors. Hard and soft armors are basically used to control the stream bank erosion. So these are the rocks and armors which are present to ultimately lessen the impact of water moving through this water body. And this is another example. This is avoiding of gully erosion. You can see here large rocks are used to control the upside effects of gully erosion in bare soil. So these are called riprap, and ultimately these are grass sod. So ultimately it helps in controlling the gully erosion in bare soil. So these are some of the ways to control the soil erosion. And again, the trapping the sediments, you can see here we are using the straw at the end of the site to slow down, and these are the straws to end of the site to slow down and let's run off while retaining the sediments. And here you can see this is another trapping sediment. So it is a sediment retention pond. This is a sediment retention pond, and the pipe at the upper ends allows excess water to flow out. So basically you can see there is an inflow of water from this place, the water carrying all the sediments, so it deposited here, and ultimately when the water level rises above a certain point, this is the pipe at the this is a pipe through which the excess water flows flows down or flows out, leaving all the sediment. So this is an example of trapping the sediment. So these are couple of ways to control this uh, soil erosion. Okay, so what are the other means of soil land degradation? Obviously, mass wasting is another mean of soil degradation, and it is basically the downhill movement of unstable soil along the regolith. And basically, it is of three types. One is soil creep, the second is mud flow, and third one is landslide. In case of soil creep, it is basically slow and downward movement of soil carving the trees, and mud flows are basically partial liquefaction of soil and their moderately rapid movement due to loss of cohesion, and landslide are basically sudden shear failure and causing rapid downhill movement of the soil. So in the next slide you will see the pictures of these three different processes. The left one shows the soil creep in UK, England, and this is the second one is shows the mud flow in Colombia, and finally the third one is landslide, and landslide is very much visible throughout the world, and this landslide can also be visible extensively in different hilly areas of India. So, guys, we have finished this lecture finished this topic of soil erosion and land degradation. The next topic will be starting is universal soil loss equation, and the universal soil loss equation will be covering these concepts. First of all, what is universal soil loss equation and how we calculate this universal soil loss equation, and what is the revised universal soil loss equation. So let us start with the universal soil loss equation. So you can see it is basically you remember if you now you have understood that a number of environmental factor causes soil erosion. It is not only the water, not only the wind, different types of other practices or management practices in the field are also important for soil erosion. So, based on this relation, this universal soil loss equation is developed to calculate the amount of soil loss, and this is basically this A equal to the equation is A equal to R into K into LS into C into P, where A is the predicted annual soil loss and R stands for rainfall erosivity, K stands for soil erodibility, and L stands for slope length, A stands for slope gradient or steepness, and C stands for cover and management, and P stands for erosion control practices. So, rainfall erosivity is basically comes under rain related factor, whereas soil erodibility, then slope length, then slope gradient or steepness, and cover and management basically comes under soil related factors, and these erosion control practices comes under the land management factor. So, you can see here basically we are considering both rain related factors, soil related factors and land management factors while calculating the annual soil loss in the universal soil loss equation. So, let us see in details how we can what are the different factors. So, this universal soil loss equation basically predicts the amount of soil loss by sheet and reel erosion in an average year for a given location. So, that is fine. So, this we use this universal soil loss equation to predict the amount of soil loss through by sheet and reel erosion. We know about the sheet erosion, we know about the reel erosion. Remember the sheet erosion, where there is a sheet of soil being lost as a result of water activity, and it basically occurs at the higher slope and higher position of the of a slopey land, and ultimately the reel erosion is the creation of small channels through which water moves the soil sediments, and these universal soil loss equation is helpful for calculating the amount of soil lost by sheet and reel erosion in an average year for a given location, and it can show varying combination of soil land management factors contributing to erosion and hence aids in decision management. As we have seen, it is considering both soil factors and then land management factors as well as rainfall factors for calculating the total soil lost, and the final also there is a disadvantage, and the disadvantage is basically it cannot predict the soil loss for Gari erosion. So, this is the disadvantage of universal soil loss equation. So, let us go ahead and see individual factors in this RKLSCP. So, let us start with the rainfall erosivity factor. So, rainfall erosivity factor or R is is an important factor for calculating the soil loss. So, remember that rainfall is a primary cause of erosion by means of detachment, transportation and deposition of the sediment. And the amount of soil eroded depends on the amount, intensity and seasonal distribution of the rainfall. Obviously, when there will be torrential rain for a short period of time, that will cause more erosion than gentle rain for a long period. So you can see not only the amount but also the intensity is also very important for creating this soil erosion, and also seasonal distribution of rainfall. If it is evenly obviously the soil erosion will be different when they are concentrated at a particular season or they are evenly distributed throughout the year. So we have covered the R. Now how to calculate the R? So raindrops have raindrops have kinetic energy, and obviously larger the drops means more the energy. So it is an index of kinetic energy of all the storms occurring in a particular year is summed to give an annual index of R. So the annual index is then average for many years to obtain R for an area. An intense unexpected storm causes high variability in rainfall intensity. So that is how R is basically calculated. So you can see this shows the influence of R factor on runoff, soil loss and P loss. So as you can see in the x-axis the R factor is given, and R factor is quite increasing in this direction, and in the y axis runoff is basically shown. So as the R factor is continuously increasing, the runoff is getting increased. Not only the runoff is getting increased, but also simultaneously soil loss is increasing, and also phosphate loss in kg per hectare is also increasing, because in case of runoff the soil moves from one area to another area, including the nutrients. So you can see with the increase of runoff R factor, obviously the runoff of soil and phosphorus, soil and runoff, soil loss and phosphate loss also increases simultaneously. So the second factor is soil erodibility factor or K factor, and soil erodibility is the soil inherent susceptibility to erosion. Remember that it is the amount of soil loss per unit of erosive energy of rainfall in a standard plot, and high infiltration capacity in highly stable soil contain iron and aluminum oxide have less erodibility factor. So obviously this erodibility factor varies from 0 to 0.1, and this erodibility increases when in this direction. Obviously the erodibility increases in this direction. So when it is 0, obviously less erodibility, and when there is 0.1 it shows the greater erodibility, and this is the soil erodibility factor. Now, soil erodibility factors also depends on several aspects. For example, there are several factors which increases K or less resistant to erosion, or factors reducing K are also there. So let us first discuss what are the different factors which increases K, the value of K, that means increases the erodibility. For example, high silt and high silt and sand content. The second is expansive clay. Third is presence of impervious soil layers. Fourth one is blocky and platy or massive soil structure. So high silt and sand content, obviously the water holding capacity will be less, and obviously the detachment will be much more pronounced in this case of silt and sand content, because there is no cohesive force or there is no attachment or formation of aggregates due to the absence of clay or organic matter. Now the presence of expansive clays, like 2:1 montmorillonite is an example for less resistant to erosion, because whenever they rise they creates different types of large cracks, and as a result there is always chances of erosion. The presence of impervious soil layers and this blocky platy massive soil structure, it helps it basically hinders the movement of water into the soil, and as a result there is the excess of water goes through runoff and ultimately eroding away the soil. So obviously when there is a blocky, platy or massive soil structure, there will be less water movement and the water will be moved away through runoff, creating more soil erosion. And factors, there are several factors which reduces the K, and ultimately increases resistance to erosion are soil or high organic matter. Obviously, when there is a high organic matter, that will increase the infiltration of the water into the soil, and as a result of that, there will be less amount of runoff. There is non-expansive K, expansive K, and like kaolinite is an example of non-expansive clays, which helps in reducing the soil erodibility. And finally, the strong granular structure, obviously they helps in more water movement. It is and as a result there is less erodibility of soil. So these are different factors which are responsible for either increasing or decreasing the soil erodibility. Let us see the topographic factor. The topographic factor is basically denoted by L and S, and LS represents the influence of length and steepness of the slope on soil erosion. Obviously, you can see the LS can be calculated by using this formula, where soil loss from a given plot over soil loss from a standard plot, and the standard plot is obviously 22 meter long with a 9% of steepness, and longer the slope of given plot, greater will be the chance of accumulation and concentration of runoff. And with increase in the slope length and steepness, LS increases and hence the erosion. So obviously, when the increase in the slope length, the L factor increases, and also when the increase in the steepness, that is S factor, these LS increases and ultimately increasing the soil loss or soil erosion. So let us see the relationship between LS factor and slope gradient for three types of sites. You can see here there are three types of site. One is low erosion site, that is rangeland, and the second one is the moderate erosion site, that is tilled row crop lands, and finally there is a high erosion lands, there is a freshly disturbed sites. So in all these cases, you can see here, as we increase the slope gradient, obviously, and the slope length, these are basically slope length 25 meter, 50 meter, 100 meter, 150 meter, 200 meter. For all these cases, with the increases of the slope gradient, the topographic factor LS is continuously increasing, because both the slope gradient is increasing as well as the slope length, that is L, also increasing. So ultimately the topographic factors is also increasing in all these three conditions. So for example, it is a 25 meter the slope length, then 50 meter, then 100 meter, then 150 meter, so and then 200 meter. So it is quite expected. Similarly, here you can see it is for 25 meter, then 50 meter, then 100 meter, then 150 meter and 200 meter. And in case of freshly disturbed soil, obviously we will have the same trade, where it is a 25 meter, then 50 meter, then 100 meter, then 150 meter and 200 meter. However, you will see that the slope is quite high in case of high reel and inter-reel sites as compared to low reel and or inter-reel sites, or in other words, in high erosion sites, the erosion or the LS factor will show the more steeper increase as compared to the low erosion sites or rangelands. So remember that in rangelands or low erosion sites, soil steepness has high influence on erosion than the slope length, and so that's why whereas freshly excavated disturbed land, slope length has a greater influence on soil erosion. So that was quite quite evident from this two different plots. For example, in this case, slope gradient is more important, here the slope length is more important. So the another factor is C factor. So C is basically coherent management factor, which basically shows cropping, how much, what is the percentage of soil cover is present. So you can see cropping system and vegetative cover affects the soil erosion, and this C is basically calculated from this formula, where C equal to soil loss under given condition over soil loss in bare soil, and you can see in C will approach 1 under less vegetative cover or bare soil. So obviously it will tends to one when there is both soil loss in bare soil in both these condition, and C will be less in case of covered soils. So you can see here the relation between the ground cover percentage and erosion. So obviously the erosion continuously decreases or exponentially decreases when there is an increase in ground cover. As you can see here is a 5% cover, then 20% cover, then 40% cover, then 60% cover, and 80% cover. So ultimately the idea of showing this graph is to convey this message that greater the ground cover, lesser is the erosion. So as the ground cover increases, obviously there will be lesser erosion. So also remember that undisturbed forest and dense grass avoid they avoid erosion at the best. Obviously undisturbed forest, so you will see less amount of runoff in those areas which are covered with forest as well as dense grass. And in arid lands, even a small amount of shrub can reduce erosion drastically, because in arid lands most of the soil are susceptible to erosion, high amount of erosion, because there is very low amount of soil organic matter, ultimately exposing all the soils to the erosive action of either rainfall or wind, either water or wind. So in arid lands, even a small amount of shrubs that can help in erosion, reducing the erosion drastically, because they will help in attaching more soil particles and resisting their movement through runoff. And in cultivated lands, forage crops can prevent erosion, and finally cover crops are grown primarily to prevent the erosion. So you can see this is an effect of increasing the shrub density on runoff in a semi-arid region. So in the x-axis, basically this is a shrub density and per hectare, and obviously soil in y-axis this is soil and runoff. So you can see here, as the shrub density increases, obviously the soil loss is decreased exponentially, runoff also decrease exponentially, and also sediment also decreases. So obviously the increasing shrub density has a greater impact in reducing the soil loss, runoff and sediment, and ultimately preventing the soil erosion. So you can see gully erosion in a bare soil. Obviously in the left picture you can see this is a gully erosion in a sorry this is a gully erosion in a bare soil, and water is muddy as it carries the soil. And here you can see clear water channel in a grass covered soil. This is another strategy to reduce the surface runoff, because we call it grass channels or grassed waterways, and these grassed waterways ultimately helps in removing, or ultimately helps in preventing the movement of water, movement of soil particles along with the runoff water. So these are an effective management practice for reducing the soil loss through water erosion. So let us go ahead and see what is the P factor or support practice factor. So support practice are done to reduce the erosion are also taken into account in the P factor. So P factor basically calculates by using this equation, where P equal to soil loss under given support practice over the soil loss if row crops were planted up and down the slope. So if there is no support practice is there, obviously the P factor will be 1, and if the support practice is there, these support practice generally include contour cropping, contour strip cropping, terracing, and terrace systems, as well as grassed waterways. So you know about the contour cropping, I showed you in the last lecture, and then contour strip cropping, then terracing I have already showed you in the last lecture, and obviously I have shown you just the grassed waterways. And each support practice in the given area contributes to this C factor also. So these are the important factors which are responsible for calculating the universal soil loss equation. So obviously the contour cultivation, obviously crops are planted across the slope gradient to reduce the erosion, and in the contour strip cropping, narrow strips of field alternate with tilled row crops, and it basically shortens the effective field length, and the water cannot achieve high velocity with alternate fields and less erosion. So these are the features of contour cultivation as well as contour strip cropping. So these are the pictures of contour cropping with graded terraces. You can see here graded terraces. So this is the grassed waterway, and so this is the grass waterway, and runoff is moving here, and these are the contour terrace and graded channels, and obviously this is an example of contour strip cropping. Obviously the grassed waterways, these are the grassed waterways, and both these practices are very helpful for reducing the soil loss through erosion by water agents. So grass waterways, let us talk about more let us talk more about the grass waterways. So grass waterways, contour strips are augmented by grass waterways. You can see here in the left picture there is a there is no grass waterway. However, in the right picture there is a grass waterway, and you can see the difference in mud flow in these two conditions. And this grass waterways consist of permanent sods established in a shallow channels, as you can see here, and they carry water from the field without creating the gullies. So they are very helpful for preventing the gully erosion, because they help in reducing or restricting the movement of runoff, which carries away soil particles and ultimately creates the gully erosion. So there is another universal solveness equation, we call it revised universal solveness equation, or RUSLE, or this RUSLE or RUSLE is the computerized version of universal solveness equation, however constantly improvised. And this revised universal solveness equation also considers the interrelationship between various factors, and it takes into account the seasonal and temporal changes and numerous sub factors, and obviously more stations are taken into account for averaging, and specific corrections are applied for unique scenarios. So let us see the universal soil loss calculation and subsequently the revised universal soil loss equation calculations. So if we consider a land of Marshall Siltrum, so it is a particular soil series, and it is clean tilled and fallowed. It has a slope of 6% and average slope length of 100 meter. R is 2550 from map, we have already got it, and K is 0.044 for this area from Weissmeyer and Smith scale, and LS factor is 1.7, high yield or internal ratio on bare soil, and low cover, and hence C is 1, and up and down tillage down the hill, and is P equal to 1. So we will all know the factors. So basically we will be putting all these values in this universal soil loss equation. So you can see R values we have put 2550, K stands for 0.044, LS stands for 1.7, C stands for 1, and P is basically 1. So we are ultimately getting 291 megagram per hectare, or 85.2 tons per acre. So let us consider the same thing with the revised universal soil loss equation. So let us consider the same soil as left with the same R and K values. However, let us assume that the crop rotation is done here and mulch is left into the soil. Hence, C values will change from 1 to 0.13. Also, they are planted on the contours with terraces. So this also we are also taking this into account. So therefore P is basically right now 0.4 instead of 1. So LS will now reduce to 1.4, that is moderate yield to internal ratio. So ultimately using the same equation R, K, LS, C and P, we will be getting this 2550 multiplied by 0.44044, then 1.4, then 0.13 into 0.4. So we are getting 8.2 megagram per hectare. So ultimately it is 3.4 tons per acre. So you can see that using the revised universal Solers equation, we can take into account different aspects, or different, we can take into account different management practices or modification in the management practices, and you can see the ultimately the quantified amount is different in both universal Solers equation and revised universal Solers equation. So guys, we have finished this lecture, and let us wrap up here. I hope that you have learned something new in this lecture, and in the next lecture we will be starting discussion about the conservation tillage. And till then, goodbye, and let us meet in the next lecture of week 9. Thank you.